Welcome everybody back. Mr. Clark here going over similar triangles as well as geometric means. I've already set up a little bit of this problem, or at least this lesson for our visual piece. We can save a little bit of time. I've got a box of information here going over some stuff. Referring to the altitude, again, just as a reminder, altitude is a line drawn straight down. I did not tell the way I thought it was going to. There we go. Straight down from the right angle to the hypotenuse. So if we do an altitude of a hypotenuse, it creates three triangles which are all similar. Summarizing that statement here. Just a bit of a review. This is the original triangle right here. That's this whole thing here. And I'm saying that this angle B is the same as the angle B here. I put numbers in randomly. I said 60. It could be, maybe it's not. But if that's the case, this has to be 30. Notice this has to be the angle of this one, same as this one, because they are pulled from the original triangle. And if they're both 30, that means this is 60. We said this and this are the same because they're both the same. That means that's 60, that's 30. We've proven that these three triangles are similar. Again, all triangles add up to 180 degrees. We are using what we call the angle postulate, or AA postulate, to create similarity or to show and prove similarity, and that works just fine for us. What we're going to do is start talking about geometric means, but first let's look at ratios, because that's something that we know we can do with similar triangles. So we're going to say, there we go. If I want to say that AD, so AD pulled from the original triangle here, but the original green side there, we're going to say AD, which is the long leg of the green triangle. We're going to put that over CD. CD is the long leg of the blue triangle. It doesn't look like it in my image here. It doesn't have to necessarily be the long leg that we're calling it that. Then I'm going to do the short leg of the green triangle. Happens to be the same thing as the long leg of the blue triangle. That's okay. And that's going to be over DB. Notice this scenario here. When we talk about geometric means, this is the algebraic view of a geometric mean. What it means is if we take, like, for example, 3 over 9 is 1/3, and 9 over 27 also 1/3. But if you multiply 3 times 27, that gives us 81, and the square root of 81 is equal to 9. A bit on a geometric mean. Geometric means are built as, let's say, a to the 1 times a to the 2, or it's not a to the 2, a sub 2, a sub 3, all the way to whatever term you want to go to. The geometric mean multiplies those together, and then whatever that last value is, the number of terms inside is the number that sits as our root. So for our example, we only have 2 terms, square rooted. If there were 10 terms, we'd do 10. An example of the use for geometric mean is really typically used when we talk about change in rate. So if you have a stock portfolio, and over the course of 5 years, the rate fluctuated, going up 20%, it went down 10, up 30, down 15, went up 5, from whatever it was at, we can take all those and multiply those rates together, take it to the root power, or the nth root, or whatever, we said 5 years, so to the 5th root. That's the rate of change on average each year. If you were to take that rate of change, or that percentage increase, and multiply it by the value 5 times, it would get us to our end goal. It's a great way for us to analyze and compare between different stocks or different stock portfolios, and lots of things like that. It can be valuations on a piece of art, or something that you have a car that's the rates changed and fluctuated over time. We can determine what that average rate is, and that's exactly what this is used for. But again, all this is similar triangles. So let's go into an example. So I've got an example here. I'll zoom in a little bit just so that we can see. There we go. So we have three triangles, and we want to identify similar triangles and sketch them. Technically speaking, this problem originally wanted us to look for H. So we're trying to solve for this. Notice we have some information to do that. Only one side is going to give us the information we need, though. And so what I ended up doing is I said, well, we're going to set up a ratio, 165 inches, over the similar triangle next to it, which is 152. And then we had 64 over H. Again, with this, something that I want to kind of focus on real quick is when we do ratios, we want to make sure that we are setting it up. Let's see here. This right here, this right here is one triangle. I'll use better color there. This right here is the top is one triangle. I guess maybe I should use the actual color for what we had. This is this triangle here, and this is this triangle here. A little messy on there, but the reason I'm showing this is when we look at like our setup and our ratio, we are looking for our original triangle that we're using for reference as this piece, and 64 also comes from that. So this side, in this case the hypotenuse over hypotenuse, and we use short side over short side. That's how we're setting it up for ratio. That's just the way I'm setting it up. There are other ways to do it, but that's what I'm doing. That's how those numbers come in. It will work every time if you want to consistently just do it that way. That's okay. So when we set that up, we get 165H is equal to 152 times 64. I know I didn't use the units in there. That's okay. I know at the end what I'm going to use for units. Now we know we can divide that whole thing by 165. So this is a product. So in our calculator, we're going to go ahead and do that here. I've already messed with numbers, looks like. So we have 152. We're going to run that by 64. And that's going to be divided by 165. I want the complete answer, which I have as 58.95. If we were rounding to the nearest tenth, we would just say 59. Again, we could check that. We could use that information to now find that third side. If we wanted to, we could check it against this one and use that same setup to see if this is the same. It should be, because this side is sharing this side right here. Notice this side would be here, and there would be a line drawn just like that, and that's our H value that we're actually solving for. You can't see it on here, but we can now. That's this side right here. That's this side right here. A bit on the geometric mean again. This is the setup for it. In a right triangle, the altitude from the right angle to the hypotenuse divides the hypotenuse into two segments. The length of the altitude, this area right here, is the geometric mean of this area and this area. We can go and create that, which I'm going to do here in a second. In fact, actually, let's just do it now. If we go and create that here, I can draw a triangle. I'm going to call this A, B, C, D. And I'm going to say this right here is the square root of A times B, where A is here. Now, there's another piece of information here. You can memorize this. You don't have to. But that's just found by taking this side and referencing this information of the smaller triangle and the smaller triangle here. There we go. And so you can memorize this. It will work. Again, though, it's just simply found by creating ratios between corresponding sides. So if I was to go and look at this side, that's a times b, square root of a times b. And if I look at this side, I can then compare to this side over here and this side if I want to. Any setup I want to do there, and I can actually calculate it out. But again, if you want to memorize that, that's fine too. That's where all these calculations are coming from. So you can use that going forward on this. A little different here because all we don't have this information, we don't have this information here or this information here. We have the total. We have a plus b. That's okay though. You can go ahead and use that formula if you want to. That's fine. We're okay with that, but we don't need to. What we're going to do is I'm going to create 3 triangles. And I'm just going to use those, so it's kind of a nice little place here. Right? Yeah, cool. That's not what I'm going to do. I'm going to create 3 triangles. And we have our setup here. This is a right angle. That's a right angle. This is 5. This is x. We don't know what this is, but that's okay. I'm not solving for it. And then we know that this is 12 and this is 13. So what we have is the hypotenuse of the large triangle is 13. The hypotenuse of the small triangle is 5. 13, 5. And then we have the we have the long leg of the large triangle, which is 12. And we have the long leg of the smaller triangle, which is unknown. 13x equals 60. And we can calculate that. 60 divided by 13. And that gives us x equal to 4.61 or 4.6. And that works for us just fine. That's really this lesson in a nutshell. It is similar triangles with geometric mean. Again, you can look at that x value here in this example as geometric mean. The geometric mean, again, if you take any number, so a over b is equal to b over c. B is equal to that geometric mean, which is really just the number that satisfies both those ratios. It's just that value that would work for any scenario. So again, 3 over 9, 9 over 27, that would work. And it's that number that's going to satisfy that solution. If you have questions, please ask. I hope this works for you. I know it's kind of a complex, messy little piece. You're welcome to just use the formula and memorize it. That's fine with me. But it's called the geometric mean. I just look at ratios. That, for me, similar triangles and ratios is just that much easier. So, best of luck. I will get another video here for 7.4 shortly, and we'll be ready to go for that.